Welcome everyone. Today we're very happy to have Douglas Stanford from Stanford, who's going to tell us about comments on firewalls from wormholes. All yours, Douglas.
Thank you. Thank you very much for the invitation. It's a pleasure to be here. This talk is based on a paper from a little over a year ago with Jin Yang, and it's related to some previous work, some older work by Lenny. It's very closely related to some work by Phil Saad, and also some work by Luca Martinez and Gabor Sorosi. Okay, so I'm sort of a pessimist, and my assessment of our work is that it has a maybe, I'm not sure, maybe 25% probability of being pretty much wrong. We're basically wrong. The likelihood that it's moderately wrong depends, I guess, on what you mean by moderate. But maybe let's say, maybe at least 50%. And this isn't because of some concrete problem that we found. It's just that I've been thinking about this over the last year, and I have not managed to sort of answer all the questions I have about it. So then why am I talking about it? The reason I'm talking about it is because I think it's really important, and also because I hope that maybe some of you will help to resolve these questions one way or the other. Okay, so what is it about? Our paper is about something called the typical state firewall paradox. And roughly what this problem is the following question. If we consider a black hole in empty de Sitter space, a large black hole in empty de Sitter space, then at fixed energy it has a finite entropy. And therefore it has a well-defined notion of typical states. So it makes sense to ask the question, suppose we take one of these black holes and we put it in a typical quantum state. What is it like? What is the state like? In particular, is there a firewall in a state? Is there no firewall? Something I should have said earlier in making this chart is that Jin is not so much of a pessimist as I am, and he also understands this much better than I do. So I think he would give more optimistic probabilities here, and so you should take his input more seriously than mine in any case. Okay, so that's the problem, the typical state firewall paradox. And we're going to try to address a baby version of that, baby version of the typical state firewall paradox, which has to do with time-evolved Thermofield double states. So the Thermofield double state time t will be defined as the following thing. It's a sum over all of the energy levels of e to the minus beta over 2 plus it times n of these states. It's an entangled state of the two black holes or the two boundary systems. And as a parameter t, which is how much we've evolved the system, let's say on the right side or the left side would be accurate. Okay, and Thermofield double states look like this. This is what the quantum state looks like if t is negative. It looks like the state of the gravity here on a slice like this, crossing the two-sided black hole. And this slice, if t is large, is very long. Like you probably know this already, just telling you the length of this thing is very long. As we increase t towards 0, the length decreases. So we have this very, very long Einstein-Rosen bridge. As time passes, it's shrinking. It's getting smaller and smaller and smaller. Reaches some minimum size at t equals 0, and then it increases again. It gets longer. And so in the contraction phase, we describe this as a white hole. A white hole, in this context, means that the size of the Einstein-Rosen bridge is getting smaller. It's getting shorter, and the black hole is when it's getting longer. And this geometry, this is a classical geometry, which is related to the state. The geometry predicts that it's a white hole if t is negative, and it's a black hole if t is positive. So the question we would like to address is what does a typical superposition of these things look like? Of the energy levels and stuff. In particular, is it a black hole or is it a white hole? Okay. So the classical answer from this geometry is that it is a black hole if T is positive and it is a white hole if T is negative. The reason this is a paradox is that what happens when we increase T or decrease T, when we change T, is we adjust the phases multiplying these states. That's all that happens in this superposition when we adjust T, we change the phases. And if we take T very, very, very large, then what we've done, assuming these energy levels are appropriately sort of random, we're just going to be multiplying these things by random phases, different random phases for each term in the superposition. And that will also be true if we take T very large and negative. We'll just get a state like this, which is a random superposition of n times n bar with random phases in front of it. That's what the state will look like if we evolve very far to the future or very far to the past. And that's what we mean by a typical superposition. Okay, so the answer should be the same. The answer should be the same if we evolve the state very far into the future or very far into the past. Because in both cases, the state is just this thing with random phases. And so the reason this is a paradox is that is a contradiction with this geometry, where there's a big difference. If T is positive, it's a black hole. If T is negative, it's a white hole. Okay. Now, why this is related to the firewalls is the following. Suppose we start with one of these states. So forget about this yellow guy for a second. The thing that I wrote up there could be obtained by acting with e to the minus I h right times t on the Thermofield level. So suppose we start with one of the states, and now we perturb it on the left side. So we act with some operator on the left side. Then let's consider the two cases separately, when t is positive or t is negative. So if t is positive, we have this slice up here. We act with this perturbing operator. It creates some disturbance in the geometry. But if we have an infalling observer, I'll run the green falling in here, then they don't see the particle. On the other hand, if t is negative, then we take this infalling observer and they fall in along this trajectory, and they do see the particle. And in fact, if the time t is large and negative, then the center of mass energy in this collision is exponentially large. So this is a version of a firewall. If t is large and negative, then the infalling observer falling into the geometry associated to this state experiences a firewall. Okay, so the naive prediction of the classical geometry is that if t is positive, then they fall into a black hole and there's no perturbation, everything is fine. If t is negative, they fall into a firewall. Yeah.
Always under problem in this picture. If you just do a propagation over the temperature of the working radiation, it's very small.
Okay.
And that's, I thought that would typically change some microstate to the other microstate, because microstate corresponds to different configuration of the working radiation zone. It's not really a single-sided kind of picture. Okay. You just have it. If you just put down more, like high energy I or something, really something you can view as excitation over the semi-classical background. Yes. Then those states need not be necessarily typical state. We're talking about typical state is kind of active states. You just excite, you go outside the typical state. And then for the because I can get like half of the black hole, half of the white hole, no problem. But why are you saying firewall?
Yeah, the point I'm trying to explain here is that if you start with a white hole and perturb it, it becomes a firewall.
That's fine. That's fine. That's
so the typical state problem, the problem of whether the Thermofield double evolved for large time is a black hole or a white hole is equivalent to the problem of whether these types of states are firewalls.
Okay, if it's excited.
Yes.
Okay, that's what I mean. Okay. Yeah.
So that's the problem that the problem I'm trying to address is this problem. whether the Thermofield double state evolved for a long time as a black hole or a white hole, and the application of it is whether when you perturb it, it's a dark hole. This is not a completely typical state, but it's a baby version of the typical state here. Okay, so the idea. The idea, and this is like most of the good parts of this work. This is really due to Janine. The idea is that small wormhole effects could lead to a correction where, let's say, let's suppose t is greater than 0. We could have the probability that the state is a white hole is something that is small. I'm going to write the answer that we get, but e to the minus 2s. Times t squared. So the idea is this, that even if t is positive, there could be a small but non-trivial probability that the state would be a white hole. And if we make some kind of extrapolation of this formula to large times of order e to the s, then perhaps this probability could become of order 1, perhaps even 1/2. So that if we evolve the state very far into the future, the state has a high probability of being a white hole, even though the classical geometry predicts that it is black. And that would resolve the tension between the future evolving to the past. Okay, so that's the idea that we're going to try to analyze. And we're going to analyze this in JT gravity. We're going to analyze it in JT gravity using the Hilbert space of an open universe. Okay, so that's the Hilbert space that you get when you cut the geometry open along a slice like this. So that's cutting the geometry open in the Lorentzian signature, but we could also consider a Euclidean signature, let's say this disk topology, and we could cut it open along a slice like that. And it's the same Hilbert space that appears, slicing the disk open and slicing this Thermofield double state. Okay, so this Hilbert space is equal to the span of some states L, where L means that the integral between the left and the right boundaries has length L. That the geodesic distance between the two boundaries is length L. So L is the geodesic length from left to right. Okay, and acting on this Hilbert space, we can define the energy. So, particularly the left and right ADM Hamiltonians for this gravitational theory. So the left and right ADM Hamiltonians acting on this Hilbert space are actually equal to each other, and they are the following: L squared plus e to the minus L. So this is what the Hamiltonian looks like acting on the L Hilbert space. So it looks like a non-relativistic particle with an exponential potential. So the eigenfunctions, so let's say the eigenfunction L with E, so the E eigenfunction in the L basis is a Bessel function. Okay. 2I square root E of e to the minus L. And these wave functions are basically like e to the I PL plus e to the minus I PL for L greater than 0. We're going to use this notation where p squared is equal to e. So let me let me draw it. Yeah. I sort of screwed up the boards here, so it's not possible to see what the board is visible. But okay, I'm going to show you some sketches of these wave functions now. But the important thing is that we have this Hamiltonian, which is like a non-relativistic problem. Maybe I should draw like a non-relativistic problem where we have some potential that's growing like this. And so the wave functions are going to be like some wave functions that are decaying in this region, and then they're oscillating in this region. And in the region where they're oscillating, they look like a superposition of these terms, right moving and left moving pieces. Okay, so let's discuss these wave functions. So first of all, let's take a state where we take a superposition of different energies around some reference energy P naught. So psi naught of P is just some wave packet that gives us approximately a well-localized distribution in energy. And if we look at that wave function, and then we look at the psi of L squared, it's going to look something like this. So L will be small for negative L because of this exponential barrier that I've just drawn as like a hard wall. And it will be small for large L because of the cancellation between the different momenta, and will be sort of localized at some point here. Okay, now what happens if we evolve that thing forwards in time? So the energy is P squared. So this is like a first year quantum mechanics problem of the particle on the half line, free particle on the half line. We take a wave function like this, we evolve it with Hamiltonian, P squared, and it moves to the right. So this thing in principle is a superposition of right and left moving pieces, but the left moving pieces bounce off the wall, and the right moving pieces just move to the right anyhow. So the whole thing is just going to move to the right. Maybe the shape will change a little bit. So we're going to end up with a wave function like this, and it's going to be P to the location that is like P naught, the central value of the momentum, times T, moving to the right. Okay, and so that means that in this state, the length is growing linearly in time. So that was what we had expected from before. The length should be growing proportional to T if T is large. Now if T is negative, then we get this opposite picture. We'll get a wave function like this that is moving to the left. And so this one here, wave function that is moving to the right, this corresponds to a black hole. And this one here with negative T, with a wave function that is moving to the left, this corresponds to a white hole.
Yeah. Is that, that's a hard column for L equals 0.
It's not L equals 0, it's L equals logarithm of E.
But it's a hard wall.
It's not exactly.
Oh, I see. So okay, that's what it was. So
yeah,
that's not hard.
You know, if this was a different kind of plot, we would write a better formula for the Bessel function. This is the kind of plot where we write that formula for the Bessel function. So. Okay, so yeah, thank you for the question. Okay, so that's just translating this picture, we're just reproducing this picture here in terms of these wave functions. Okay, now let's return. I will come back to these later pictures in a second. Okay.
So is it some big numbers, some delta function somewhere here?
It's not a double function. It has some width in both energy and length, but fairly small. So in the semi-classical limit, like small.
That's
right. Yeah. So
some width in there. Okay, the full degree.
Yes. Yes. Yeah.
And just to be sure, right now we're in the canonically quantized description.
Yes.
But eventually wormholes will be important.
Eventually, wormhole will be important quite soon. Yes. And then we get into all kinds of trouble. So right. Okay. So now let's discuss. Now let's discuss the basic idea, which is baby universe emission. And this was described in this paper of Phil's, where he used this to complete the two-point function. We're going to use it for a related problem. So let me just first draw a picture of, this is a kind of vague picture. Hopefully this kind of topology is clear. This is what people call a handled disk. It's a genus 1 surface with one boundary, and then we have like a handle. So I mean the two-dimensional surface here, not anything filling it in or outside. Okay, so if we think about this thing, then let me draw two spatial slices connecting the following boundary points. So the relation of this thing to black holes or whatever for the moment is not explained. I'm just trying to introduce some notation for this kind of surface. So we have two boundary points here. And we could imagine a spatial slice that, or a geodesic that connects those boundary points like this. We can also imagine one that connects them like this. It goes in here, like that. But notice that the purple cut does not divide the surface into two pieces. So to divide it into two pieces, we can add also this baby universe. So baby universe means a closed universe, a closed geodesic. So we can think about this, the bottom half of this geometry, as a tunneling process that starts with a single open universe, that is a single segment here, this green line, and it ends with a single segment like this, and also a baby universe. So this geometry describes baby universe emission. It's like a tunneling process where you create a baby universe where there was none before. Okay. We're going to draw this kind of geometry, the lower half of this thing, in a simpler kind of notation like this. We're going to draw it like this. We're going to be drawing these kinds of drawings. So what do I mean by this? The bottom half here is the boundary, portion of the boundary, connecting the left and the right dots. And the L is this thing, and A is the length of this closed geodesic. So this is the shaded region here is topologically the same thing as the bottom half of this geometry. Okay, so this describes tunneling. I guess I should also draw the green one. So this green one we won't actually be using, but just to make it clear, I'll draw that one over here too. That one is like this. Yeah, and so the green one and the boundary are homotopy to each other. Okay. Okay, so now let me describe the sorry. No, there's one more. So in Phil's paper, he worked out how this baby universe emission works, and there's a nice way to analyze it, which is to think of this thing as a piece here with the L prime, and then we glue it to some operator L A. So we just decompose that. We decompose this thing here into two pieces. There's the part between the boundary L prime, and then there's this part here, which has two geodesic boundaries, three geodesic boundaries, one L prime, one L, and one A. So this part here corresponds to everything between these lines. And in the formalism that Phil developed, you can think about this thing here as like an operator that is acting on the Hilbert space, L prime. We have this Hilbert space we've been working with so far, where this ADM Hamiltonian with wave functions and everything exists. And this thing here that acts on it is like an operator that acts on that Hilbert space. And the important thing for us is the following. Basically how this operator acts is it gets in the energy basis, it acts simply as multiplication by cosine of A times P. It's not exactly right, but it's good enough, times e to the minus x, good enough for our, good enough for the level of precision we're going to be discussing. So this operator acts on this Hilbert space somehow, turning L prime into L, or fixed to A, and the way it acts is multiplication in the energy basis by this cosine. Okay. Right. So let's now go back to the pictures of wave functions.
You're really working on the P basis, right?
Yeah, P or I mean, it's I could have written square root of E here.
Yeah.
But
P is positive, right?
no, P is not, P is, well, yeah, yes, yes.
Formation.
Yes, yes. Yeah, P is positive, but we include both right moving and left moving pieces, which are the pieces that would have the negative P. Because of the boundary condition, we have only the sum of them.
I mean, you're going to allow A to be. I'm confused by the fact that your length somehow at some point will formally become negative, right?
Yeah, I'm going to explain the fact that they're not really negative. Something is negative. It's not.
But A here is restricted, for example, to be positive.
Yeah, A is positive. Yeah. The point of me drawing these wave functions is it's supposed to clear up exactly the point that I think that you might be worried about. So let's see if it works. So the goal of what I want to do now is I want to act with this operator on the wave functions that we were just discussing. So previously we discussed the wave function with no time evolution. We discussed the wave function with positive time evolution, with negative time evolution. Now we're going to take a wave function with positive time evolution, that was this one, and we're going to act on it with this operator. So we do Berkeley universe emission, and then we see what the wave function looks like after doing that. So here's what it looks like. So the state we have now is the state we had before, this state here. That's the initial state with the time evolution. And the new thing is we multiply by this operator here. So the cosine has two terms.
Yeah, I'm so sorry. Yeah. Previously you had some quantum mechanics problem that you completely solved, right? And that solution didn't involve acting with this operator, you just let it go and it would move to the right.
Yes.
And so how do we think about the inclusion of this operator? Is this way you include some, you modify the theory by including some complementary effects?
Yeah. That quantum mechanics does not represent the full quantum gravity dynamics. That quantum mechanics just describes the time evolution of the Thermofield double state on the disk topology. It just describes the dynamics of an open universe. But the full dynamics could involve open universes and also tunneling into baby universes. So the tunneling into baby universes can be described within that. It can be described as an operator that acts within that Hilbert space.
Yeah.
That's the.
And is this is it easy to see that this is like the next most important thing you need to be thinking about as you're sort of extend the theory to these non-competitive effects?
Yeah, this is in a theory that does not include time reversal, then this is the first thing. This is the first non-perturbative effect that you would have multiple baby universe emission, but the lowest order non-perturbative thing is single baby universe emission. Okay, so we multiply by this. The cosine has a sum of two terms. The term that is going to do all of the interesting stuff for us is the e to the plus I AP. So I'm going to ignore the e to the minus I AP term. So let's just multiply by e to the plus I PA. Okay, so we take this wave function here and we multiply it by e to the I PA, and then we look at the result. And there's two cases. So if A is small, in the sense that if A is less than P naught times T, then what happens is this P just gets translated to the left a little bit. It's translated to the left by amount A. It's translated to the left by amount A, this is just translation operator. So the new position is P naught times T minus A. That's what happens. The thing is still moving to the right. Okay. If A is bigger than P naught times T, then naively you want to take this thing, you want to translate it farther to the left than the boundary conditions allow. And what happens in that case is it bounces off and ends up here, but now it's moving to the left. So it ends up at a position that is A minus P naught T, and now it's moving to the left. So if you evolve further in time, it will bounce off, and then we'll end up out here. It will, end up kind of looking like this thing, moving to the right, just delayed by a. Okay, so that is the
State divided by P is a kind of some sort of transformation, Fourier transformation, probably of the state L.
yes,
And the state L is the defined kind of nominable length L.
yes.
There is a state with the baby universe including, it is maybe still like a space bound by P complete, including, because it is canonical formulas.
Yeah, we're doing canonical formulas, and we're only paying attention to the open universe part. And we're dealing with the baby universe part as operators acting on the open universe part.
The operators still enable a space bound by just P.
Yes. Yes.
So that's some, okay, so the state with the baby universe is a crazy superposition of the state without that. These one things, because it's still superposition of B, that's still superposition of the original level.
You mean because the original state was a superposition of P? Yeah, the original state was a superposition of P, and acting with the baby universe creation operator does not change that fact. It's still a superposition of P.
So that means that the baby universe, existence of the baby universe is some representation, some crazy superposition of the things without.
Oh, I see what you mean.
Same space.
No, it's yes. So, okay, I think I understand the confusion. I've been a little bit imprecise. So far we're paying attention to only the open universe part, but there is a baby universe, and we're going to have to deal with it in a second. So we're discussing what happens to the state of the open universe part, but there's also a baby universe over here now. We're going to have to do something with that.
Okay, so if the universe is created, this part becomes that, and back times some universe.
Yes.
Okay.
Yeah. Exactly. Yeah. Thank you for the clarification. Okay. So the important thing is that this is still a black hole state, but this is a white hole state because the thing is moving to the left. So what has happened, that a formula that kind of unifies both cases is the following formula. You can think of the age of the black hole after the emission. The age goes to the original age before the baby universe emission minus something proportional to A. So it's not the length that gets negative, it's the age that we're getting, the time. And if A is big enough, then it can turn a black hole into a white hole.
That wasn't in your original presentation, right? This way of presenting it makes it look much nicer than having to talk about negative, right?
Yeah, I think that's yes. It was not. Yes, I agree.
So it took you a year to figure this out.
Well, we actually have that formula in our introduction.
At least essentially saying that.
But the way okay, so let's use this to calculate the probability that the black hole is really a white hole. So let's So now we're going to deal with the thing Sonoran was mentioning. We're going to deal with the fact that we still have this baby universe. So the way that works is we calculate basically this full path integral, and that in our language looks like this. We have an A here, we have an A here, and in this geometry, the two baby universes are glued together. So we should take this circle here and glue it to that circle, and if you glue those things together, you get something with that topology. So that's the full computation we're trying to compute. And so let me give you some, so there's some factor e to the minus 2 times s. We had a factor e to the minus s, that operator there, e to the minus 2 times s. And then we're going to have some integrals over the perimeters in the gluing. So there's an obvious integral of something we can integrate over, the size of the baby universe. And there's a less obvious thing we should integrate over, which is when we glue them together, we could twist one of them by some amount before gluing them together. So that's A, and there's also a perimeter S we should integrate over. We should make some Yeah, so that's what this path interval looks like. Let's further restrict it to, let's look at the probability of a white hole. So that will be this thing restricted to having A greater than P naught times T. Because that was the case where we ended up with the white hole. So we're supposed to take this integral here, we should restrict A to be greater than P naught times T. And there's one other restriction, which is this twist S. It cannot be more than A, because if you twist one circle by more than A, then you've it's the same as twisting it by less than A. So we should restrict the twist to be less than A. But otherwise, we integrate these things from 0 to infinity. And so that's the problem with this thing is that it's infinite, because this A could be arbitrarily large. There's no upper limit to how large it's a lower limit. There's no upper limit to how large A can be, so it's infinite. Okay. So that's bad news. And this is the beginning of the subtleties in this analysis. So any more questions on this relatively safer part? Yeah.
Is this not a state with fixed L still?
Say with fixed L?
Like the L here, is that not a parameter that would limit how big A can be?
If we fixed L, but we don't, there's no reason to fix L. So we should integrate over L, and when we move these things together. So you're right that the value of L will depend on A, but there's no reason that we should restrict L. If we did restrict L to something, then you're right that it would never be an operation here, then it will be fine.
So there's a wave function in A, right, which is suppressed in large A.
That's the, yeah, but that's before we act with this. So after doing the baby universe emission, this thing could end up way out here, very large L. The wave function could be beat to extremely large L. So if we somehow truncate it to some finite region of L, then the location of this hump can only be between 0 and L. And so the divergence that we get would be regulated. But the divergence is associated with the fact that if A is very, very large, it would be arbitrarily large, this thing could be way out there. The length would be extremely large, but that's still a white hole. So it still appears to be. So let's now, okay, so the basic problem, okay, so I should say that up to now this is, I think, just pretty clear. From this point forward, I don't actually know in principle what the right thing to do is. I don't know in principle what the right thing to do to correct this infinity is. We're going to do something, and it's subject to the probabilistic constraints that I gave before. I'll now try to explain.
Sounds like what you're saying is that you have to regulate in such a way that if you take the tables infinity, like 50%, 50%, that's the requirement you have to put. Like normally it's the same thing at the time you also symmetry. You just put that as a constraint or some.
Well, that wouldn't be enough, because if T is large but not infinite, then probably not 50-50.
Yeah, but in a limit that we have to in a limit that we have to regulate in such a way that all of the limit is important.
Yeah,
that's just regulated, take the T in such a way that it has to.
That's an interesting idea. It's
because that's the kind of symmetry.
Yes.
And that's the thing you have to put, and then any other conclusion forms. Like that's a anomaly. Right?
Well, that does not. Well, okay, and probably you might like the answer to that, but you still want to know why you have to put this constraint. Or what is it that actually deals with this thing? So
maybe part of the definition of it.
I don't think we should adjust the definition of the theory by the answers we want to get. We should figure out why it's infinite and how to properly deal with the infinity. And hopefully that will give us 50-50 in the end.
that would be great, but in an anomaly case, for example, was not. Like you have to put some condition like to preserve vector current, and then everything else follows. Then normally for unstable current is fine. That was a choice. So it's a definition of theory. It's because that's a symmetry. It's a symmetry.
Maybe you're right. Yeah, I don't know. That's well, one point that they remind me of that I think is interesting. So Yasser mentioned maybe it's 50-50 probability with black hole versus white hole. I think it's interesting that actually, if you look at this wave function has that property. Naively has that property that this branch is right moving. This is a white hole piece, and this one is left moving. This is a black hole piece, white hole piece. So if you look at this wave function, it looks like it is for a specific energy, like a particular energy. It looks like it's 50-50 white hole. It's only when you take this position in time evolvement that the black hole or white hole part wins. Okay, so you might think that the whole. Let me not say more. Okay, let's instead talk about a similar infinity that arises in a completely well-defined context and how that infinity is dealt with, and we'll see if we can figure out something to do based on that. So, okay, so the other infinity comes in computing what's called the volume of the moduli space of this surface. So we want to compute what's called B1 as a function of B. So now B will be the, yeah, it's not quite this surface. Let me draw this a bit better. It's a surface that looks like this, where we have a geodesic boundary of length B here. So this is a closed geodesic. And you can also have some big universe of psi k. And the volume V1 of B is defined as the volume of the moduli space of surfaces with geodesic of length B at one side. So that's the only thing you're imposing. You integrate over things with this topology. Because if you like the JT gravity path integral with boundary condition is the closed geodesic of length B. Okay, so what that is it's an integral using what's called the Weil-Petersson form. It's an integral dA ds of this thing. So this thing. So this is called the three-hole sphere. So we've cut this thing open along this geodesic, a three-hole sphere, where one hole has length geodesic of length B and the other two have length A. And so this naively, the volume of this moduli space is given by starting the three-hole sphere and then integrating over the length A and the twist in order to glue it together. Now, it turns out that the partition function of this thing is just 1. So this whole factor is just 1. So independent of B and A. So naively, the volume V1 of B is just equal to integral dA ds. And that would be integral dA ds from 0 to A, and from A to 0 to infinity. And naively, that's also infinity. Okay, so what is the problem with this computation? The problem with this computation is that what's actually being computed here is not the volume of the moduli space. We're not just decomposing, what's being computed is an integral over the volume of the moduli space and also how you cut it open. So there are different ways of taking this exact same surface and cutting it into a closed universe and some closed universe. So we could take some A cycle that goes like around here. And then we could cut it open in this way. And this integral is counting both the integral over the moduli space and the sum over different ways that you can cut it open. And it's the sum over different ways that you can cut it open that is responsible for the infinity. The integral over the surface itself is something high. It's actually it's not easy to compute to take that into account and compute the actual volume of this moduli space. But here's one way that you can do it in the limit where this B parameter is very large. I'll describe a simple computation of this thing when the B parameter is very large, and then we're going to use that to go back to the firewall stuff. Okay, so when the B parameter is very large, then it turns out the volume of this surface remains finite. So it's a finite volume surface with some very, very large, very long boundary. And the only way that can happen is if the surface is like a thin strip. It's a thin strip between this boundary. It has fixed area, but like a very long length boundary. So it has to be very thin strip. And what that strip looks like is the following. So in the pictures that we've been drawing before, it looks kind of like this. We take this B to be very large, and then we take this A. We have some picture like this. And we glue together these two A circles, which can be very large, and this small thin strip between. We could draw a geometry though where these things have been glued together as the following thin strip. So we can take this geometry, so the boundary here is B. And now there's no gluing required. This is the whole strip geometry, and this is a genus 1 surface. So we can attempt to integrate over the surface by integrating over the family of these strips. Integrate over the volume of this moduli space, integrate over the moduli space, I should say, by integrating over the space of these strip geometries.
So if you modify,
You need to connect it to that side.
if area has some coordinate areas of you kind of switch to the stage.
Yeah, this is not completely obvious, but let's check something about it. So let's check that it has one boundary. So okay, so we follow this line around.
That's what I was worried about. That's what we want.
It has one boundary.
Yeah.
And
Here's also it looks like a 3, so I don't know, I missed it, what you those are.
yeah, so for example, let's draw a couple points. You know, this and draw a line between them. This will be relevant later. That you can take, for example, to be these points and a line running between them. And the A circle is a closed geodesic that does not intersect that dashed line, and that's going to look crazy. I'll draw it for you, but it looks like this. Okay, so we did find a closed geodesic that does not intersect the dashed line, so it's looking pretty good. And well, I promise you that this is a geometry.
This is the entire boundary.
Yeah, that's the entire. So there's no gluing is required now. Now this strip is the whole thing. So, right. So okay. Okay. So let's think about this. So this strip geometry basically has 3 parameters in it. It has the lengths of these 3 strips. There's y1, the length of this piece. There's y2, the length of this piece, and then y3. It's the length of this piece. And okay, what can we check? So let's look at y1 plus y2 plus y3. Well, that's the total length of this thing. That is equal to b over 2, because the boundary has the boundary is on both sides of the strip. So the total length of the strip times 2 is equal to the length of the boundary. So y1 plus y2 plus y3 is equal to b over 2. And this measure, dA/dx, is actually equal to just the measure dy1, dy2, dy3 is restricted to this this condition. So we can redo our computation here. This thing, this is actually equal to integral dy1, dy2, dy3 times a constraint that says y1 plus y2 plus y3 is equal to b over 2. Okay, and that's equal to b squared over 8. So these are not integrated from 0 to infinity, but they can't get too big because their sum has to be no bigger than, but has to be equal to b over 2. So this is almost the right answer. The right answer for the volume of the moduli space in the large B limit is 1/3 of this. And the 1/3 is because there's a cyclic permutation symmetry between the three strips. Okay, so that is one way to view the volume relation space. Okay. Now we're going to go. Now we're going to go back to firewalls. So as I said, I'm not sure what the totally principled thing to do is here. So we're going to do something, but I'm not sure what the in principle correct thing to do is. What we're going to do is to basically assume that the infinity that we got in our computation here is the result of a similar overcounting problem, where what's happening, what must be happening, is that this integral over the genus 1 surface that represents the beta universe emission, we must be overcounting different ways of inserting our open universe over space. So, let me try to draw that more. So let's go back to this picture with the big boundary. And what must be happening is we're doing some integral over these geometries, and we're summing over choices of this L surface that we call our open universe over space. We're taking, let's say, this one, and maybe we're also summing over an L slice that does something like that. Or some that like goes around and many times and whatever else it does. So the infinity that we're getting must be due to the fact that we are summing over L slices more than one L slice for the same geometry. We should not be doing that. That's what got us into trouble with modules.
So if I think of this geometry as somehow representing an operator that the BIM universe emission operator, what you're saying is it really represents an integral in some sense. I mean, it can act on, you can slice up in many different ways where it represents the universe emission starting from various kinds of
Yes. Yes.
But that's not a maybe, right? That's definitely
That's definitely true.
That's definitely an overcounting there.
Yes.
So what you made it sound like you're not sure if this, if you should include this effect.
Yes. So
we have to.
We have to include something here. What I'm not sure about is what, in a situation where geometry has multiple possible geodesics that can be used to define a spatial slice, how do you pick which one defines the infalling observer? We have, let's say, two choices. New maps here. Let's just take two choices. So we have this one, and we have this one. So here's L. This is the nice one, and L prime. So both of these are defined open universes connecting the left and right boundaries, and they could be continued forwards and backwards to make some Lorentzian geometry. And we could imagine that the infaller falling from the right boundary, which interior do they fall into? Is it the one associated to L prime or the one associated to
I don't understand what the infaller, why we have to discuss the infaller here. I thought you would just say that, just the same way that you could say, okay, this geometry represents an operator that would correspond to baby emission starting from various different L's.
Yeah.
If you want to fix L and you want to know if a baby universe is going to get emitted, then you're going to have to look at various different geometries which contain that L in a different way, and some overall effects in some way. But I don't understand why we have to discuss the infalling observer. It's just a question of how it evolves, right?
But I think the question is not, the infalling observer is needed because we need some probability. It seems that there should be a finite probability associated to the infalling observer. That's a physical question. We're trying to find it. And
I thought the infalling observer is sort of not really. You're just interested in what happens to the wave function, like what values of, whether it has more or less support in contracting or expanding solutions.
And in particular, well, let's say that, but also what the length is. You're right that in principle we could try to answer it without determining the length, just whether it's expanding or contracting. I think that would make this a little bit easier. let's be a little bit more detailed and say that we also want to know what the length is. And then L and L prime are different. So which is the right answer?
This isn't the wave function, right? I thought this just represents something. The wave function will tell you if some wave function is a function of L, right? I thought you were computing the time evolution on it.
This is like a contribution to some kind of state with a projector onto L state. This looks like this kind of where we fix this length L. And we integrate over geometries with some fixed length L here. So it looks like, this looks like the probability distribution for a length. But that is not super well defined because there are different geodesics with different lengths. I think as the problem is, I don't know how to answer that general question as stated. I think for the particular case we're analyzing, it's a little easier. So but there's a general problem here that I do not know how to answer, even in principle. Yeah.
That's a more basic question. If you sign up this infinity, if you put in a second board,
sorry.
This infinity is also coming from this kind of overcounting.
Yes. Yes.
Okay, then what I said doesn't, so you don't need a renormalization. Then what I said is not.
Yeah, we should not, we should be able to fix the overcounting
just by doing.
something.
Yeah, okay.
So I'll show you how we propose to fix it.
Yeah, okay.
And
Okay. But I was just saying that what I said was possible only if the intrinsic infinity remains, not just by overcounting. Then you need to define the theory you need to that's the case.
I feel that the intrinsic infinity better not remain because the quantity we're trying to compute is finite.
Yeah, but in intrinsic infinity you need to do renormalization. Then this dependence on the theory or definition of theory may come in. But if you could resolve it without
I don't think this is a quantity for which you should need to do renormalization.
Yeah, so that was my question. Then what I said doesn't work.
The approach you're advocating was taken in the paper by Eliezer, Messiaen, Sorosy, in a somewhat predictable context. They did a type of renormalization and got some finite answers after renormalization.
But you claim we don't probably need it.
I hope that there's a way of doing it that does not require that.
Thank you. Yeah.
Okay. So here, what we're going to do is the following. So in the application, we're interested in the case where the time parameter t is very large, very big time black hole, and we're also interested in the case where the big universe is very large. So we're in this strip kind of thing, where the geometry has very, very long boundaries and has fixed area. So we can use this strip picture. So it sounds very complicated to try to resolve this problem, but we can do it in the simpler context of this strip geometry. So that will help us a little bit. And we can use the following geometrical facts. The main one is that in the path integral for this surface, the region that is relevant is when the b parameter. So in principle, we have a complex geometry that we're integrating over. This is a complex geometry, which analysts could continue this thing to like a over 2 plus it, so it's a complex geometry. However, you could take a contour for the complex geometry where all the topology is real and is glued to the complex boundaries across a real geodesic of length b. And the b is 2 t naught times t. So that is the result of a separate geometrical calculation, which I'm not going to show you. So that helps us to translate the problem that we're trying to solve into the strip diagram. Because now we know what the b parameter is. And so what we can do, that's one point. The other point is that the actual asymptotic boundary can be thought of as close to that b boundary. So we can think about the asymptotic boundary as being close to this boundary here. And the asymptotic boundary has two parts. there's the part corresponding to the cat, which I'll draw with a squiggly line. And then there's the part corresponding to the bra. And the part corresponding to the cat is close to this part of the B surface of this strip. So that's basically what the space-time geometry looks like. The cat part of the boundary is along this locus here, some strip, and the bra part of the boundary is along there. And the final geometrical fact, which is relevant, so these parts are not conceptual, these are just technical, these parts. So that's why I'm going over them I'm not explaining them. These parts are just technical. Is that the relevant part of the geometry is where the endpoints, where the transition between the bra and the cat takes place, have to sit here, between these points. They have to sit at these locations here where the strips come together, where the three strips come together. So those are three facts that just allow us to translate the thing we're trying to compute into a strip land. Now that we're in strip land, what we want to do is we just want to integrate over this strip geometry and consider what the possible spatial slice could be, the spatial slice L. So you can consider different possibilities. You could consider a spatial slice that goes up this way, connecting those two. It turns out that that one is not on shell, so it does not contribute. You could consider one going down this way for the same reason, it does not contribute. So you can consider a spatial slice that goes between these like this. And that's the one that contributes. And the overcounting problem, the divergence that we're getting, is because we're also summing over spatial slices for the same geometry that do this, that follow this curve, and then they go up and around and come back. And they do that any number of times. They go around this thing some number of times. So they're built out of this simple one that goes between this point and that point by adding some loops, approximately loops. That's the full characterization of these geodesics. The full possibility L and L prime are all like that. Those are the only things that are true. So our proposal is just to only include this one, not to include these other ones that go around and around. That's basically our proposal, is that those other ones are overcounting the same geometry. It's the exact same geometry, it's just a different choice of L slice on the same geometry. And our proposal is just to include this one. And okay, if you do that, then the result is this formula here, where you replace B by 2 times P naught times T, and we forget the 1/3 because the permutation symmetry is broken by the choice of the strip that the orange curve goes on. So we end up with probability white hole meaning well, there's eta minus 2sp, which also comes with a 2 pi squared. And then there's this factor here. So it's 2t squared over 8. And that's the result that I had quoted at the beginning. The t squared is minus 2s.
Is that the same as the short slip?
It turns out that it is the same as the, okay. That's a surprisingly difficult question to answer. Following reason. Yeah, the answer is yes and no. It could be that there are configurations where there is a shorter length here. It might be that this length is shorter than this one. But this one does not contribute, it's off shell. So it's a weird situation. It can happen in Lorentzian geometries where there could be a shorter geodesic, but it's off shell. It does not contribute. So this is the shortest length that contributes to the 2 point function.
So what does it mean for a geodesic to be off shell?
Yeah, what it means is that you could integrate over the locations of these boundary points. Like I told you that the relevant configuration is where the transition between the bra and the cat happens at this point here. But really in the path, that really integrate over where that happens. And for the geodesic that is coming out this way, as you move it this way, you get a phase factor e to the 2 energy times the distance you moved it. And so it's oscillating. For the geodesic that comes out this way, moving it up and down, you do not get this phase factor. It's basically like pinned to this location. So the geodesic that goes this way does not have an oscillating phase associated with it. The geodesic that goes up this way does have an oscillating phase associated with it. Does not contribute. So like the shortest unshelled geodesic. Sure. Now there's a criterion that was proposed for a similar kind of issue by Pennington and Whitten, which was to take the shortest, not the shortest geodesic, but the shortest a cut through the geometry that corresponds to the shortest combination of the length of this thing and the length of that thing. And that would be different. So they proposed that in a different context. It was not too closely related to what we're studying. But if you do suppose that the shortest such L plus A combination always defines the correct interior for the infaller, then you get quite different results. So that just illustrates the kind of sensitivity of this to that choice. Okay, I think I'm out of time, right? So, yeah.
I think I'm misunderstanding something. So if I believe that doing these cuts with different numbers of cycles around first and then going around the one path that contributes gives me the same answer, I can see why just with that fact you would say, I only need to include one. But if I do these different cuts and then I do my Lorentzian evolution afterwards, don't I get different space times?
Yeah, so this is a good question. And it turns out that what you get is you get different space times, but they're all white holes. So it might be that if you're only trying to calculate the probability it's white hole, this is very similar to Raphael said earlier. Forget the length, just whether it's a white hole or a black hole, then that criterion does not distinguish between these different curves. So you might say that means that's some kind of justification for this. Okay, so the possibility that prescription is a little bit wrong is, I would say, the 50% probability that our work is moderately wrong. The larger failure mode, where it's like mostly wrong, would be that you're just not supposed to include these at all. And that none of these qualify as a valid interior for an infault. And the reason why I think that is only 25% likely is that we can try to falsify that pessimistic scenario using the traversable wormhole protocol. And basically what we can do is we can check from the boundary observable the probability that there is a short white hole. So if the white hole is a white hole with a very long length, there's no way to tell that from boundary observables, because like the black hole the wormhole is so long there's like nothing that is sensitive to that length from the boundary perspective. But if the white hole is quite short, then there are observables that can detect it. And the traversable wormhole is one such thing, and it basically it predicts that you see somebody falling in, then we'll see the fireball. It's a weak fireball. It's a short white hole. It's a very weak fireball, but it predicts they will still see it. The problem with that is that only covers a very small part of this probability with one smaller factor of t. So it is only at most a very small probability. So it could be that most of the probability mass here is still wrong. We don't have a way of verifying that part.
So the remaining 25% is that probability mass is accounted for by something that is not this.
Yeah, but that for the remainder of it, this is just wrong. So there's some small part where it is fairly short, where it seems to be right, but maybe it's wrong for larger. So that's the reason why I assign a relatively high probability of being wrong, 25%, is that I have not been able to figure out in principle what we're supposed to do to solve this problem. This is some kind of hack that sounds sort of plausible or not, depending on your views. I'm not sure. I'm not trying to sell it too hard, but I'm not sure the principal thing that you're supposed to do to try to actually settle the problem. Okay, so I've gone over, but thank you very much.
Questions for Douglas?
said something about real geometry there.
Yeah.
Can you explain that again?
Yeah, the overall geometry is complex.
Yeah.
But you can think about that complex geometry as a complex like trumpet part, which is glued across a real geodesic to a real rustic topology. And yeah, so that allows us to use this real strip picture. The kind of subtle thing there is that then you have this Lorentzian boundary over here that I'm somehow telling you the Lorentzian boundary can be identified with locations along this Euclidean strip geometry.
Well,
That is true, but kind of weird.
yeah, and so those other geodesics, they're all real as far as this part to the right of me is concerned.
Yes,
right?
yes.
They're-
So the geodesics could have a small complex part that like they're making for a small complex part for like the trumpet region, but the long parts of it.
And is that, do any of them remain completely real all the way to the boundary? Like, liquid?
Yeah, so that's, you can, yeah, this is, what you can do is you can insert in this path integral a projector onto the length B, and L being real. And then it will be real, the other ones will be slightly complex.
This choice would be,
Yes.
like, I see.
The one that you will, yeah.
And doesn't that sound also like a plausible thing as far as Pauling observer and
I don't think so, because you could also pick a different one to be real, the other one to be slightly complex. That would be another valid contour choice for the path integral on this geometry. So, which geodesic is exactly real is not. It depends on the contour. Path integral contour.
one of these other ones?
One of the other ones, but this is one is exactly real. The way to see that is that here in this computation, with no, we're being very naive with the topology distribution converting over L, it's always exactly real, and I've claimed that that's because of an overcounting problem. So that exactly real geodesic I'm talking about must actually sometimes be one that lines around in a weird way and overcounts. Questions? If not, let's then go again.